Ever stop to think what's really happening when you boil a pot of water? It seems pretty straightforward. Bubbles and steam, right? But underneath the surface, there's some incredible physics at play. And today, we're going to pull back the curtain on this everyday wonder.
Yeah, it sounds like a simple question, doesn't it? But trust me, the answer is going to take us on this amazing journey, deep down into the microscopic world of particles and energy. All right, so to really get a grip on this, we're going to follow a water molecule on its entire adventure. We're starting with a solid block of ice, and we won't stop until it's turned into invisible steam.
I mean, we've all done this, right? You add some heat to ice, it melts into water, and then that water boils away. But that's just what we can see. The real story, the really cool part, is happening at a level that's totally invisible to us, down at the molecular level.
Okay, so let's do it. Let's zoom in, and I mean way in. We're going to see exactly what those individual little H2O molecules are doing at each step of the way. Because, folks, this is where the magic really happens. Okay, so check this out. This is basically the secret life of water molecules. When they're in solid ice, they're all locked up tight in this perfect, ordered structure, kind of just vibrating in place. Then, as a liquid, they've got enough energy to break loose and start sliding past each other. But as steam, whoa, they're like tiny little rockets just zipping around with total freedom.
So what's holding them together in the first place? Well, it's something called intermolecular forces. The easiest way to think about them is like tiny invisible magnets that hold all the molecules together. And if you want to change states, go from ice to water or water to steam, you've got to find a way to break that magnetic pull.
And that's exactly what heat does. When you add energy, you're not just making things hotter. You're actually giving those molecules the power they need to fight back against that glue, to weaken it, and eventually to break free. So heat is literally the key that unlocks their freedom.
All right, so if adding heat is the cost of freedom, how much does it actually cost? Let's look at a heating curve. Think of this graph as a kind of roadmap that's going to show us exactly where all that energy we're adding is going at every step of the journey.
So here it is, the whole journey mapped out. You can see these sloped parts, A, C, and E. That's where the temperature is going up, just like you'd expect. But look at sections B and D. They're totally flat. So what in the world is going on there?
And this right here is the big puzzle. Think about it. We are constantly pumping heat into this system, but during melting, and then again during boiling, the thermometer just stops moving. It doesn't go up at all. So where is all that energy going? It has to be going somewhere, right?
And here's the answer. All of that energy is being spent on one and only one job, breaking those intermolecular forces. It's not being used to make the particles move faster, which, by the way, is what temperature actually measures. Nope, all that energy is being paid as the price to physically change the state of the water.
So that first flat part on our map, that's the price of melting. Scientists have a name for it, the heat of fusion. It's the exact amount of energy you have to pay to turn a chunk of solid ice into liquid water.
Now, on the sloped parts, where the temperature is actually climbing, we use a different calculation. The amount of energy it takes to raise the temperature is determined by something called specific heat. And then we get to that second flat line, and you'll notice it's much, much longer. This represents the heat of vaporization. It's the massive energy investment you have to make to turn that liquid water into a gas.
And get this, look at the difference. It takes almost 7 times more energy to boil water than it does to just melt it. Why? Well, think about it. Melting is like just loosening the grip between molecules. But boiling, you have to completely sever those connections. You're setting them totally free. This incredible amount of stored energy is why steam is so powerful. I mean, it literally powered the Industrial Revolution. It's also why a steam burn is so much worse than a burn from boiling water.
Okay, so all that energy we just spent to create steam, it didn't just change the state of the water. It gave those molecules a brand new kind of freedom. And with that freedom comes a completely different set of rules. So let's dive into the laws that tell us how gases actually behave. So to make sense of how gases work, scientists came up with a really useful model. It's called the kinetic molecular theory. It basically simplifies things by pretending we're dealing with a perfect or ideal gas. In this ideal world, gas particles are like microscopic billiard balls, constantly moving, totally random. And pressure? That's just the combined effect of all those little particles smacking into the walls of whatever container they're in. For this model to work, we just have to assume that the particles themselves are tiny and that they're moving so fast that they don't really attract each other.
Now, this model might sound a little too simple, but it is incredibly powerful. It lets us predict what a gas is going to do when things change. And we don't need any super complicated math, we just have to think, okay, what are the individual particles doing?
Let's try it. For example, imagine we've got a sealed container, like a can, and it's full of that steam we just made. What do you think happens if we start heating it up?
Well, that extra heat energy makes those little water vapor particles go absolutely nuts. They start zipping around way faster, which means they're slamming into the walls of the can both harder and more frequently.
And what does that do? It means the pressure inside the can goes way up. This shows us a really basic relationship. As temperature goes up, pressure goes up. It's a direct result of all those amped up particles banging against the walls. It's really that simple.
And here's the cool thing. You can use this exact same line of thinking to understand all the different gas laws. All you have to do is ask yourself 2 questions. 1, how does this change affect the particles? And 2, what's the result of that new particle behavior?
So, we followed a single water molecule all the way from being locked in a vibrating solid to becoming a free-roaming gas, and it's all driven by the flow of energy. The next time you boil a pot of water, just remember what you're actually watching. It's a beautiful demonstration of fundamental physics, playing out right there on your stove.
But that leaves us with one last question, doesn't it? We've explained the rules for a perfect, ideal gas. But what makes a real-world gas, well, real? What happens when those tiny attractions and the actual size of the particles do start to matter?